Awesome. Thanks so much for taking the time to listen to the workshop. Feel free. I know that I think the hackathon just started, so please feel free to work on the project. This is just a quick overview of LlamaIndex, and we'll go a little bit in depth into some of the components that we offer that could potentially help you on this project as well as for in the future, if you decide to build an LLM application, thinking about how to incorporate some of the functionalities of LlamaIndex within it. And then there will be some tutorials within the slides so that you could follow them and play around with it if you wish, whether in this hackathon or for future hackathons. Awesome. I think, Ravi, I couldn't quite catch what you were saying, but I guess like maybe for questions, one thing we could do is you could field them or we could put them in the Zoom chat as well. But in any case, I'll just go through the slides. And then if you guys have any questions, please feel free to put it in the Zoom chat. Awesome. Okay. Without further ado, let's go to the slides. Okay. So the goal of this is to just give a quick overview of LlamaIndex and to describe both the high-level vision as well as give some in-depth use cases about some of the functionalities that we offer. The key goal of LlamaIndex is to be a central interface between LLMs and your external data. And so I'll try to share these slides out as well, and so I'll ping organizers, and hopefully there's a bunch of links embedded in these, so hopefully you can play around with some of the demo notebooks and tutorials. The GitHub link is linked below, and so that's the central point if you want to clone the repository and play around with the Python package, and also take a look at the documentation. Awesome. So the quick context is that LLMs are a phenomenal piece of technology for knowledge generation and reasoning. They're pre-trained on large amounts of publicly available data. And so if you think about all the cool stuff that you can do with language models, you can do stuff like question answering, text generation, summarization, planning, a lot of other things. People are coming up with new use cases every day, the coding, for instance. And so there's a lot of just fundamental generation and reasoning capabilities baked within the language model. But I think the key question is just how do you augment it with data that's private to you, both for an individual as well as for an enterprise. And so, you probably have just a lot of files laying around like PowerPoints, Excels. If you use Notion or Slack or Discord, you have a lot of data that's locked within different servers. And if you are an enterprise and you have a massive data infra pipeline setup, you have a lot of data silos and databases and vector stores. So the question is, how do you best augment the LLMs with this data? I'm sure you guys all know this, so I'm not going to go into this too in depth, but one of the paradigms for inserting knowledge is to just like fine tune or train the model to do gradient updates on the weights and to bake knowledge into the weights of the network. For a variety of purposes, this fine-tuning process doesn't work super well right now for a lot of users because you need to prepare the data. There's a bit of lack of transparency in terms of how the fine-tuning process works. A lot of times, I think empirically, fine-tuning doesn't work super well, and it's actually quite expensive. There's like a high upfront cost for fine-tuning. These days, I think a lot of people, in terms of trying to augment data, is trying to augment LLMs with their own data, do some form of in-context learning. And the idea of in-context learning is basically you have this prompt, right? And so the question is, how do you just stuff the right context in the prompt so that you can basically condition the model on the right set of inputs to give you the output that you want? Just to give a quick example, I mean, if you have a Notion database of your essays, the idea is that you would have some sort of retrieval process to fetch the relevant pieces of text for the task at hand. So for instance, if you had a question and that question is, what did the author do growing up? You would have a retrieval process actually retrieve the right pieces of information from the text and put it into the input prompt in order to create this full input prompt that you would then send to the language model. So you have like a small, you would start off with an initial question, and then it would get wrapped in this overall prompt. And this would be what the overall prompt looks like. For instance, here is the context. you put the context right here, and then given the context, answer the following question. And then you put the question, and then you feed it to a language model. So I'm sure many of you might already be doing this, especially during the hackathon. There are some basic stacks with setting up a vector database with Pinecone and doing top K embedding search and all that fun stuff. And we also allow you to do that and also offer some advanced primitives on top of this as well. And so we'll spend some time talking about that. Awesome. So in terms of some of the challenges of in-context learning, I think, and just to give you a sense of some of the areas that we're thinking about on the LlamaIndex side of things is, one, how do you retrieve the right context for the prompt given the task? Is your task to ask a simple question about a specific detail? Is it to summarize over some piece of the documents? Is it to compare and contrast documents? Is it to go over structured data? The second point is, how do you deal with long context? And the third point is, how do you deal with source data that's very heterogeneous and potentially very large if you have just gigabytes or terabytes of data? And the last is, the interaction between a retrieval model and a language model leads to this complex data system. And how do you trade off between aspects like performance, latency, and cost? So that's where LlamaIndex comes in. And the idea of LlamaIndex is that it's supposed to be a key interface between your data and language models. Our goal is to make this interface just fast, cheap, efficient, and performant. And so we contain three main components. So you start with your data sources, whether they are already structured in some form, for instance, in a vector database or structured database, or they just lie around in the form of raw files. And then there's data connectors, and then there's data indices, and then there's a query interface. So these are the three main components of our toolkit, and we also offer some additional stuff on top of that. But data connectors is the way to connect your existing data sources and data formats from all these, from different APIs, file formats to our toolkit. And so we offer this through a site called LlamaHub. The next is data indexes, where you can structure your data for different types of use cases, whether it's question answering, summarization, or other types of use cases. And finally, we have a query interface where you could feed in some input prompt and obtain a knowledge augmented output. The key idea of LlamaIndex is that you can basically have a black box around your data, and it'll take in a query and it'll give you back probably like the best retrieval result and the best response synthesis. And so this is basically a service that you can wrap around in a variety of forms, and we'll talk about that in just a bit. I think there was a quick question in the chat. When you say long context, is it still a challenge with GPT-4 having 8K or 32K token size? Yeah, so it's a good question. I think there's obviously GPT-4 made the context window bigger. I don't have access to a 32,000 token window yet, but that's basically an 8x increase on GPT-3. The main thing with GPT-4 is if you try to feed in all 32,000 tokens, one, that's actually quite expensive. It's actually $2 US per query. And then the second is, depending on the size of your data, that's still not going to all fit into the prompt. Like if you just have generally a database data set of like gigabytes or terabytes of data, you're still going to need to have some sort of retrieval model, even if you want to stuff the entire prompt with 32,000 tokens. Okay. Awesome. So this kind of gives you a sense of how we position ourselves as a service within an overall framework. So at the top level, you have this outer abstraction. So basically any application framework, a ChatGPT plugin or a LangChain agent, some sort of outer loop that can go around and call us as a service. The input would be a natural language query, and then the output would be a response plus a set of retrieved documents. And so LlamaIndex would basically be the data interface or management solution across your different data sources. So it would handle stuff like data ingestion from these various data sources through our LlamaHub data connectors. And then it would also help you define index structures on top of existing stores. So for instance, databases and vector stores. And the high level idea is to just be a black box and get really, really good at, if you send in some question, we'll give you back the response and set of documents that you want. Cool. So in terms of the data connectors, you you can actually try these out at the hackathon. They're probably the easiest thing to use, like whether you choose to use it as part of LlamaIndex or LangChain or anything else. The idea is we offer over 70 data connectors on Llama Hub, and you can ingest any kind of data from anywhere. So you could ingest stuff like PowerPoints, spreadsheets, PDFs, all the way to APIs like GitHub, Notion, Discord, websites, etc. And so this number is actually out of date. We have like over 70 now. We actually have, you can actually ingest stuff like images and audio as well. I know Ravi added a ton of these loaders, so props to him for doing that. And so this is basically like, to get this up and running, it takes about like 2 to 3 lines of code for just initializing the loader class. And this is also linked in the slides as well that I can send out. But it's an easy way to just load data from any source to help you build your application. The next component here is data indexes and a query interface. So once you actually load the data from somewhere, our data indexes help to abstract away common boilerplate or pain points for in-context learning. So the idea is that you have some context window, like 4,000 tokens for DaVinci or 8,000 tokens for GPT-4. How do you basically store data that's greater than this number of tokens in a format such that you can, during an input call, you can retrieve the relevant pieces of context from your bigger knowledge corpus and figure out a way to work with the prompt limitations that DaVinci and GPT-4 have. So after you figure out a way to structure this data, the next step is a query interface. A query interface on top of these index structures helps to both, if you have a natural language query, will give you back the results that you want, both in terms of the source documents as well as the synthesized responses. So for instance, here's an index, and then here's a query interface. Given our internal wiki, write a one-page onboarding document for new hires. Let's walk through probably like the most commonly used part of the stack today, which is having some sort of integration with a vector store. So we offer that through a vector store index wrapper. And the idea is that you can ingest your data from any source, for instance, through Llama Hub data loaders, and then we would ingest that into a vector store index. And the way it works is when you input documents or nodes into a vector store index, we'll partition these into nodes with embeddings for each node. And then within the vector store index, we will basically just store these nodes as documents with an embedding associated with it. Then during query time, as I'm sure many of you are familiar with, we would take in a natural language query, get an embedding for that query, and then use that query embedding to do top K retrieval from the vector store. So basically, fetching the most relevant nodes by embedding similarity with a top K value. So for instance, if it retrieves these 2 nodes, then we would pass these 2 nodes down to a response synthesis module along with the query. So once we've retrieved the sources, we can then pass it along with the query to this black box that will then call the language model to synthesize the response for you. I'm just going to open up the chat. Yeah, okay. So awesome. So what's the best way to modify user queries, and maybe also split the query into back and forth calls? Let me get into that in just a bit. I think happy to answer some of these kind of more user related questions. And then can you share how data indexes internally works, splitting the context? So that's, I'll try to give a high level overview of how some of these indexes work right now. And then a lot of this information is present in the docs as well. Cool. Another very basic index structure is a list index. So you can have, for instance, just once you actually ingest a set of documents, a basic list structure, which will partition the documents into nodes and then store it in some sequential list. And so instead of, for instance, like a vector store, here, all you have is like a linked list of every node in the document. And by default, during query time, you would just feed every node in the document into the response synthesis module along with the query. So instead of just doing top K retrieval, you just feed everything. Obviously, this has some downsides in that it can be quite slow, especially if you feed in a lot of documents. But this is basically the default way you would do summarization, especially if you had a question that required you to go through every single piece of the document. This is probably the main index structure you would use to perform a summarization type query. Just to give you a bit of a sense of how the response synthesis module works, there's a few different modes. So once you actually have a set of candidate nodes and you want to synthesize the response, basically the idea is that you have a query and then you have a set of nodes. And one paradigm is create and refine, where you basically synthesize response over the first node given the query. And then now you take that initial answer and then pass it in to the next node. So now, you have for the first node, the inputs are the query and then the context, and then you get the context from the node and you get back an initial response. For the next node and all subsequent nodes, the inputs are the query, the intermediate response from the previous node, and then also the context from the current node. And then you just keep going for all subsequent nodes to generate a response until you finally get back a final response right here. Another mode of response synthesis is this idea of tree summarization, or some people call it like map reduce as well. The idea is that you have a set of nodes that you want to synthesize an answer over. So here, what you can do is you could take the query and then feed it into each node. And then for each node, given the query, generate an initial answer for that node. Then across multiple nodes, so for instance, for every 2 nodes, you would want to synthesize a parent answer using these 2 nodes as context. And then given these 2 nodes, synthesize a parent answer given the answers from these 2 nodes as context. And the idea is you would just hierarchically build a tree of answers until you finally get to a root leaf node answer, or sorry, a root node answer. We also, so these are some of our basic data structures. We also offer some more advanced capabilities like composing a graph. And so the value of this will be described a bit more in the use cases section that I'm about to go into in just a bit. But the idea is that you can actually compose indexes on top of other indexes. So for instance, let's say you have 3 different tree indexes, each representing a different piece of your data. You can then compose a higher order index on top of these 3 tree indexes. And in this case, it's a list index. And so in this case, basically, you have, let's say you have 3 tree indexes, each one representing some document structure or some collection of data. Then you can compose a single list index that unifies all 3 tree indexes so that each node in this list index maps to a sub-index, which is a tree index. Just to give you a sense of how this works, during query time, once you actually compose this graph structure, the idea is that you would have a query and it would first hit the list index, the top level list index first. And then once the query hits the list index, it would take that query and route it to each node within the index, similar to just a list index by itself. Once it hits each node, it would actually then route the query down to the sub-index as well to synthesize an answer. And so because you're basically treating, now each node has a reference to the sub-index that you can then get an answer from, then this means that this allows you to take advantage of the list index operations to synthesize an answer across all your heterogeneous collections of data. Because for each node in that list index, it'll call a sub-index in order to get the best, get back the response. That's a high level. Some of you might have questions. Some of this might well be detailed in the use cases as well, which I'm about to go into. But if there's still more questions, I'm happy to answer that. Going through and pass. So there's 2 more. So how can you please give an overview of how the new evaluation module works later? Yeah, sure. I'm happy to chat about that. Ravi actually contributed it, so I'm sure he can help out as well in terms of how to use it. But I can just open up a tab and we can go to a notebook as to how it works. And then how can we decide which synthesis method to use? It's a good question. I think by default, I would probably go with the tree summarize method. And then you would have to set that explicitly in the index.query call. I can link to the docs. Basically, that should describe how you can do this. But the tree summarize allows you to do stuff like you can do async in terms of response synthesis, which will make this process much faster. Create and refine tends to be a bit slower. Okay, now let's talk about one of the first use cases, which is basic semantic search. So this goes along with the idea of just how do you take documents, put it into a vector store, and then ask questions over that vector store. So here you can see that this process, one of the benefits of LlamaIndex is it pretty much takes like 5 lines of code for you to get something. And of course, you can add more customizations on top of it. But the idea is from LlamaIndex, import GPT simple vector index and simple directory reader. Then from the directory reader, you can load data and then just call simple vector index dot from documents. So this part, load data, will ingest the data. This part will build the index, and then this part will query the index, and then you'll get back a response. And so this is just a classic application of semantic search where we take this query and then we do top K embedding retrieval from a vector store index to fetch the relevant pieces of content from the text by embedding similarity. And then we would take the highest nodes by embedding similarity and put it into the response synthesis module to give you back a response. The next use case is a summarization. This is also a pretty basic use case. The idea here is that, from LlamaIndex, you could just import this. This is actually wrong. One sec. This is GPT list index, simple directory reader, and then you can just call GPT list index off from documents. And similar to the vector index, you can just call index.query. The main difference is that by calling index.query on the list index, this will go through every node, as opposed to just doing top K embedding retrieval. And so this is useful for questions like, hey, can you give me a summary of this article in new line and bullet points? And then response mode, tree summarize. And then this would give you back the response. That's basically a summary of the entire article. I cut this off because the response was way too long, but hopefully you get the general idea. We also offer some basic text-to-SQL capabilities. So actually, not just basic, we offer a lot of text-to-SQL capabilities. So this is a very basic example, but if you want to have a full in-depth guide on how to take advantage of some of this stuff, please take a look here. The idea is that, not only can we ingest unstructured documents, you can actually connect to a SQL database and then just call GPT SQL structure index from documents you can actually choose to convert unstructured documents into structured data within your table if you would want to. And if you don't want to do that and you just want to do text to SQL, then just feed in a blank document list here and then just do index.query, which city has the highest population over the set of tables that you specify. And then this will be the generated SQL that you can then execute. So select city name, population from city stats, order by population. Can we index the CSV data? This is a question from the chat. How do we ingest the metadata around the data? Good questions. We actually do also have a pandas loader. So in addition to text to SQL over a SQL database, we actually have a pandas index as well. And the difference here is that when you do pandas index.query, and with a natural language query, we'll convert it into pandas operations instead of a SQL statement. And then that will actually execute over your pandas data frame. And then how do we ingest the metadata around the data? You can actually specify metadata for each table column as well. So if you want to go into the SQL guide, it'll give you a guide as to how you can ingest, or you can actually specify just like text descriptions of each table if you want to. Next use case, synthesis over heterogeneous data. This part is actually where it starts getting kind of interesting because this starts getting into our composing a graph over your data as well. Not that the previous sections weren't interesting, but this is more interesting. This is like also interesting. So basically we have 2 data sources, for instance, one over your Notion docs and then one over your Slack docs. So Notion docs is GPT simple vector index from documents of your Notion docs. And then Slack index is GPT simple vector index stuff from documents over your Slack docs. Now, then you can compose a list index, for instance, over these two sub-indexes, right? And so you have a vector index for Notion and you have a vector index for Slack. Now you can combine both of them via a list. What this means is that when you ask a question, like give me a summary of these articles or just any sort of question, the same question will be routed to both the Notion docs and the Slack docs. You'll get an answer for each one. And then because this is a list index, what we do is we'll just combine the responses from each sub-index into a single answer in order to give that back to you. So just to give you a quick example, let's say I have two vector indexes. This is about the city of Houston, and then this is about the city of Boston. If you compose a list index over these two sub-indexes, and then you route this query, tell me the airports in Seattle, Houston, and Toronto. If only one city is provided, return the airport info for that city. If airports for multiple cities are provided, compare and contrast the airports. It's a bit of a complex query, but the high-level idea is that you want to take this query and send it down to each vector index, synthesize the response from each vector index, and then combine all the responses into one response. So here you can see the final answer is that the airports in Seattle, Houston, and Toronto are Seattle International Airport, George Bush Intercontinental Airport, Toronto Pearson. And I guess I'm missing a Seattle vector index here as well. And I guess this is actually a wrong image. Let me just, so this really should be Seattle, Houston, and Toronto. I did a minor slip up. This says Houston and Boston, but hopefully you get the general idea. Another example is that you can actually use, for instance, our query decomposition module to break down more complex queries, such as this, into a simpler one over your data source. And this works well over your composed graphs as well. So for instance, if you have, again, a vector index for Houston and then a vector index for Boston, and then you have a list index on top of both, then let's say you want to ask a question, compare and contrast the sports environment of Houston and Boston. So this is a kind of multi-part question, right? Because it involves asking the question, what is the sports environment of Houston and what is the sports environment of Boston? You send this query down. If you add a query decomposition module, then basically it'll decompose this query into, hey, what sports teams are based in Houston and what sports teams are based in Boston? You'll get back an answer from each sports team. And then this allows you to, from the list index, because you're trying to answer this top level question, like compare and contrast the sports environment, then you can finally answer this question of, hey, I have these two answers from the vector indexes. I have this top level question. Give me a final answer. Sweet. The last piece of this, which again, this is like, if you're interested in playing around with these models, like this is basically the idea of these use cases that I went from pretty simple to more advanced, is you can actually do multi-step queries too. So we have this, for instance, query decomposition module, which will break down a query into one smaller query over a single data source. Here, you can actually break down a complex query into multiple sequential queries over the same data source. And this is basically, if you're familiar with stuff like chain of thought prompting and query, like self-ask, react, that type of stuff, it really starts getting in the vein of that. But the difference here is it's very much in the context of what your data provides. So let me just give you an example. Let's say you have a multi-part question that's kind of complicated. And the question is, who is in the first batch of the accelerator program the author started? Now, this is kind of like a multi-part question, right? Because probably like the first question you would ask is, okay, well, what exactly was the accelerator program the author started? And then the next question would be, okay, well, now that you know what the accelerator program is, like who was in the first batch of that? Let's just assume for the sake of simplicity, you have one data source, like one index. You don't have like a composed graph, like let's forget about the composed graph part. Let's just assume you have a simple like vector index. And let's assume this vector index contains all the information that you need to answer this question. because this just like allows, this data source contains all the info about what the author did, including the accelerator program, who's in the accelerator program, that type of stuff. If you just ask this question by itself, the model tends to get confused. But if you have some sort of, for instance, like multi-step query decomposition or chain of thought reasoning process, then you could first ask, hey, what accelerator program did the author start? You would ask this to the data source and then get back a response. The author started the accelerator program called YC. Then you feed it to the query decomposition module again, who is in the first batch of the Y Combinator's accelerator program. First batch of YC's accelerator program, which started in 2005, included startups like X and Y. And then, okay, so you keep basically going until, you know, within this prompt and this chain of thought reasoning process, you can say something like, hey, like, have we answered all the components of this question? And if so, just say return none, right? Which means that there's no more further questions to be asked. And after answering these two components, you're basically done. The accelerator program is called YC, and then this is the first batch of YC's program. And so then after you see that it's done, you can synthesize a final answer. The demo tutorial for this is, there's a notebook, and then there's also a tutorial as well in the query transformation section. So this, hopefully, if you're interested in playing around with this, please feel free to take a look. I think Dev asked, should I just blindly do query decomposition by default for all applications? Is there a reason not to do decomposition? It's a good question. I think probably to start with, the reason I would just say, I would always start with something simple. And the reason is, anytime you add an additional module like query decomposition, it incurs a little bit of cost and latency because it makes another language model call. So it's going to add some, 100 to like a second of response time, right, to your end application. If, for instance, I think if you do want to incorporate stuff like this, though, there's just like a trade-off between the performance and the latency. For instance, multi-step query decomposition means that you're basically kind of going through this like self-loop process like 3 times, which will take a bit longer, but hopefully give you back the response that you want. The next question is, for a chatbot scenario, how should we approach it? How to use LlamaIndex or Hub? That's a great question, and that actually gets right into this. So the idea is that LlamaIndex is just, the idea of LlamaIndex is to be a really, really good tool that you could plug in to any agent abstraction, whether it's an open source abstraction like LangChain or ChatGPT as a plugin. But we have a great tutorial here on how to build a chatbot by using LlamaIndex as a tool, or even like multiple tools. And the advantage of this is you can actually define like a LangChain agent on the outer abstraction, and then you can actually define a LlamaIndex set of tools. Some of these might be simple tools like simple indexes. Some of these might be graph structures that allow you to do more fancy stuff like the compare and contrast, like query decomposition queries, those types of things. And this actually provides a very nice interface, because then you have this outer agent that's deciding what to do, and then it can leverage any one of the tools that we can provide in order to look up and retrieve information. Here's just like a simple video of this in action. And here we have like a very simple chatbot within a notebook. And we're basically asking about the SEC 10K filings here. Sweet. Another example is that you can actually build a downstream Streamlit app if you wish. We have this thing called like the LlamaIndex starter pack, which you can use to package the LlamaIndex application that you build into a Docker container, into a Streamlit application, or into, for instance, a backend server like Flask in order to build a full stack application. I will, when I send these slides, I'll link to the LlamaIndex starter pack as well, so that you can take a look at how to use it. Just to give you a sense of if you want to just like play around, for instance, with the SQL capabilities, there's the LlamaIndex like SQL sandbox, which I think my internet's a little slow, but hopefully this should load. Okay, I think it's my internet. Oh, nice. So you have like some open API key, and then you put this in here, and then here you basically can start asking questions, and then it'll convert it to SQL under the hood by using our SQL index as a tool, and then return you back a response. Awesome. So I think these slides are meant to be shared. So the idea is that I also just attached a bunch of demo walkthroughs towards the end. So for instance, how do you play around with Llama Hub? Like you can ingest data. Here's some questions over Paul Graham's essay, what I worked on. And then here's, let's try to answer some of like SEC 10K queries as well. And so all the links are here. And the idea is I will send these slides over if you do want to have a chance to like play around with some of these notebooks. They'll contain links to all the guides and notebooks so that you can take a look. And then I think there was one user request to take a look at the evaluation module. So let's just do that really quickly. I will pull it up. Okay, awesome. Great. So the idea here is that Ravi contributed this amazing module called the response evaluator module, where the idea is that you can, after you do index.query, so for instance, after you get a response from an index.query call, you can then feed this response into the evaluator in order to see if the answer is good or not. How do we check whether the answer is good? The idea is that every response that we get, we get back both the synthesized answer as well as a set of sources for the response. So the idea is that, in the case of top K retrieval for the vector index, we'll get back a set of top K chunks that we fetched from your document corpus. And then we'll also synthesize the answer as well. And one way of just checking if your answer is good is to see if the answer actually matches the retrieved sources, at least one of the retrieved sources. Because, if the answer doesn't match any of the retrieved sources, this means that, like, one, your model's hallucinating the answer. And then two, there's probably some like degradation or there's probably some thing that's not doing well in, which is that the retrieval model might not be that good, or the language model might just be synthesizing the wrong answer from your data. And so it's actually a pretty simple and effective way of just checking to see if your model is actually outputting the right answer. And the nice thing about this is you actually don't need any ground truth labels. Like you don't need like a ground truth answer given a question, like what is the actual answer they should output. You can just like check the predictor response against a set of sources that it contains, and then just use that against itself. This notebook is an examples evaluation, test NYC evaluation right here. This is actually not in the docs yet because I've been a little bit behind on updating the docs. But if you want to play around with it, this notebook should give you pretty much everything that you want. And again, huge shout out to Ravi for contributing this. Sweet. I think that's basically it. Are there any high-level questions? I do see one that I will answer, and then happy to take any more in the remaining time that we have. Let's say we have, for instance, hundreds of pages of legal text PDFs for which we want to retrieve answers to questions. How do we approach it? Should we do some sort of paragraph extraction, then index? Yeah, so I think like the way I would think about this is I would always start with the simplest thing. Just try this, or a semantic search. Just try these 5 lines of code, and then in terms of text splitting, I think you could try optimizing the text splitting a little bit so that you use like a more sophisticated text splitter. We actually just came out with like a sentence splitter today. But try like dumping it into a vector index. We have integrations with like Pinecone, Weaviate, Chroma, all the popular vector store providers. So see how that works maybe on a sample of data, given a set of questions that you want to ask. And then, if that solves your use case, that's great. Then you could just go with that. If, for instance, that doesn't solve your use case and you actually have more advanced needs that you want to add, then you would need to basically like, you would basically want to try out some of our more advanced capabilities like the graph index structure. For instance, if you want to build like a outer chatbot abstraction with like using a lane chain agent with us as a tool, you could start off by having us as a tool purely for semantic search, but then add other tools as well if you want to, for instance, define graphs over your data to help, like, for instance, compare and contrast different legal text PDFs, perform summarization, all these types of things. Hopefully that makes sense. Awesome. Any other questions? Okay. Well, I think let me just try sharing these slides. I will put them into the Zoom chat right now for those of you that are online. And then for everybody else, I'll just message the organizers with the chat, with slides. But yeah, I think that's basically it. Good luck with the hackathon. Thank you all for listening.